Hello everyone, thanks for joining us. Today we are here to present our project titled Resilient Federated Learning for AI-driven DDoS Mitigation in Multi-Cloud Networks. To give you a little brief, it's all about organizations that are increasingly relying on multi-cloud environments, which makes attackers leverage AI and large-scale automation to launch more adaptive, high-volume DDoS attacks. Traditional security models simply cannot just keep up. But our research focuses on next generation approach. We're using federated learning designed to improve detection accuracy, protect privacy, and coordinate responses across AWS, Azure, and Google Cloud. With that context, let's begin the core problem our work addresses. This is Chetan Palambati, and let me begin by defining the problem. The modern attack surface is distributed and complex. Over the last 5 years, we have seen an over 65% increase in multi-cloud adoption. Organizations are now slowly moving to distribute applications across AWS, Azure, and Google by default. While this provides flexibility, it also creates unprecedented complexity and distributed topologies with critical blind spots that adversaries are actively exploiting. This distributed setup makes it extremely difficult for defenders to maintain global visibility, leaving networks vulnerable to sophisticated DDoS attacks. Let me give you a state of the field literature review that differentiates between traditional defenses and the modern adversary. We find traditional defenses are failing against rapidly evolving threats. Legacy systems still rely on centralized monitoring, fixed rules, and strategic traffic thresholds. The issue is simple. These defenses cannot adapt to zero-day attack signatures or dynamic attack behavior. Modern-day problems require modern-day solutions. Hence, modern adversaries use large-scale botnets, automated scripts, and AI-guided traffic shaping. Their attacks are high volume, adaptive, and capable of mimicking legitimate user behavior, allowing them to slip past signature-based detection systems with ease. You might ask, why not just rely on centralized AI models? Good question. While centralized AI can detect anomalies across metrics like packet entropy and flow frequency, it introduces three major flaws in a multi-cloud world: privacy and compliance risks. Centralizing raw traffic logs across clouds violates data governance requirements and increases exposure, and followed by single point of failure. If the central model or its training pipeline is compromised, the entire defense collapses. And the other difficulty is prime target for adversaries. Attackers can inject poison data into centralized datasets, corrupting or misdirecting the model entirely. Because of these risks, centralized AI is no longer a dependable solution for distributed cloud environments. Our proposed solution is nothing but resilient federated learning, which fundamentally changes how we train AI detection systems. Instead of centralizing data, we train the model where the data already lives, across AWS, Azure, and Google. Raw logs never leave the cloud environment. Instead, only secure encrypted model updates are shared. This approach preserves privacy by design, eliminates the single point of failure model, reduces the attack surface dramatically, enables more accurate detection through diverse distributed training. Federated learning creates a collaborative defense network that is far better suited for multi-cloud environments. From here, my friend Balu will take over to explain more about our solution and its approach. Thank you.
This part includes the overall framework we developed for resilient, privacy-preserving DDoS mitigation in multi-cloud environments. The idea behind this architecture is simple. Instead of relying on a single centralized system, we spread the learning and detection across multiple cloud regions. This makes the system more reliable, harder to compromise, and better suited for real-time detection. With this approach, we are bringing together privacy, resilience, and accuracy into one unified framework designed specifically for modern cloud setups. This part includes the overall framework we developed for resilient. Here, we are focusing on how the learning happens directly within each cloud region. We have edge data collectors in Azure, AWS, GCP, and on-premise environments. They gather important details like net flow data, traffic entropy, and packet metadata, and they do some quick pre-processing to get the data ready. Each region then trains its own anomaly detection models locally. Only privacy protected updates are shared, not the raw data. So sensitive information stays where it belongs. This approach keeps data private, reduces risk exposure, and helps us catch unusual behavior right at the point where the traffic first appears. Here, we are focusing on how the after each region completes its local training, all the updates are sent securely to a federated aggregation server. This server never touches raw logs. It only receives encrypted model updates to make sure the global model stays trustworthy. It uses techniques like crim and trimmed mean to filter out anything that looks malicious or odd. Once everything is validated, the server combines the updates into a stronger global model and shares it back with all regions. This lets every cloud environment benefit from collecting information without sacrificing privacy or security. Now the system moves into a real-time detection and automated response. Using the global model, the detection engine identifies both known and unknown DDoS patterns. Autoencoders help detect new unfamiliar attacks while supervised models handle the ones we already know about. Together, they generate real-time threat scores. Based on those scores, the response orchestrator takes action. It connects with AWS Shield, Azure Front Door, and GCP to automatically apply rate limits, reroute the traffic, or update access rules. This gives us a fast, coordinated defense across all cloud environments, helping us to stop attacks as soon as they're detected.
Our framework represents a foundational shift in how we tackle the multi-cloud distributed denial of service problems or DDoS problems. We have integrated a federated learning approach. This is key for ensuring privacy preserving and scalable model training, as it allows us to train our models without ever centralizing sensitive customer data. Second, we integrate adversarial defense. This involves robust aggregation techniques, specially designed for protecting the integrity of our models. Finally, we have integrated a multi-cloud orchestration. This provides a crucial, unified, and automated response capabilities that can discuss about technical specifications and ethical design. For implementation, we plan to use a hybrid approach, leveraging multiple model types, specifically an autoencoder for anomaly detection, and a one-dimensional CNN for packet level analysis, and random forest for orchestrating on final decision. We analyze key features like packet rates, flow duration, and syntax ratios. Our training protocol uses federated averaging, typically within between 20 to 50 epochs per round. For bias mitigation, training across diverse clouds manually reduces vendor or region specific bias. Privacy protection is maintained because no raw logs are ever shared, only securely aggregated model updates are being exchanged. And for explainability, the system generates clear interpretable anomaly indicators, which are necessary for human oversight and swift security action analysis. Our approach offers significant advancements. We acknowledge the current challenges inherent in decentralized defense and have a clear roadmap for the future. The primary challenges involve overhead as federated learning introduces necessary network synchronizations, In terms of cost, the robust aggregation methods are computationally expensive, and in terms of integration, where multi-cloud security APIs often have inconsistent rate limits and capabilities. Looking ahead, our future research directions are focused on maximizing privacy and minimizing latency. First, implementing blockchain-based traceability for immutable logging of model gradients. Second, integrating zero-knowledge proofs for to achieve fully private model updates. Third, adapting the system to 5G edge computing to push detection even closer to the source for ultra-low latency. And finally, by exploring reinforcement learning to build fully autonomous and adaptive mitigation policies.